But before we get too hot and heavy into creating functions, let's talk about how we can convert back and forth between polar and rectangular coordinates. Very, very important because, yes, polar coordinates in and of itself are wonderful. Rectangular coordinates, we know what those are all about. Bridging the gap between the two is what we're going to try to do here. And this is a little twist off of what we were talking about last class when we were getting into unit circle calculations. Any point in polar space can be defined based on, again, theta and r, so distance away from the pole and the angle from the polar axis. But we could also decompose it into a right triangle x and y, with legs x and y, I mean to say. Exactamundo, right? But I'm going to take a sec and show the step that comes right before that, and that is if I'm looking at theta, I could say that the cosine of theta is equal to the adjacent over hypotenuse, x over r, and that gives us x equals r cosine theta. All right? Because a consequence of that relationship, this one trig ratio actually tells us more than one thing. It gives us more than one conversion. So if I were to take the inverse cosine of that, I would then determine that theta is equal to the inverse cosine of x over r. So I now have a way of converting r's and thetas into x form, but if I have an r and an x, I can convert it to give me a value of theta. I can do the same thing with sine. Sine of theta is y over r. And as you said, y equals r times the sine of theta. But also, theta would be equal to the inverse sine of y over r. And while we're here, might as well throw a tangent in there. Tangent theta is equal to y over x, opposite over adjacent. Now I could solve that for x or y. It's not really going to advance the plot. The only meaningful one that it's going to give me is that inverse tangent of y over x is equal to theta, or theta is equal to the inverse tangent of y over x. So that allows me, if I'm given values strictly in terms of y and x, to come up with a theta related to that. And, you know, I don't want to be neglectful. There's also the good old Pythagorean theorem. One little triangle is given all this. It's crazy. X squared plus y squared equals r squared. Take the square root, and you get r equals the square root of x squared plus y squared. Technically plus or minus, but as it's going to turn out, we're not overly concerned with negative r values when it comes to functions, so I'll show you what that means in a little bit. Algebraically, it comes out in the wash. All right, but now we have the means by which we can convert from one form to another. You just gotta kind of cherry pick which ones are the most useful formulas. All right, so we'll just kind of decide based on what we see. Find the exact rectangular coordinates of each point. So if we're looking for rectangular, what we're given is polar based on the form. It kind of makes sense because they have a degree measure in there. So I have an r and a theta. I need an x and a y. I have an equation where x is all alone on one side. X is equal to r cosine of theta. And I have one for y also. Y is equal to r sine of theta. So my R value is 3. Cosine of 270. And then 3 sine of 270. Oh, what is that? How does that work? Did I just take a screenshot accidentally? Alright, well, whatever. So what's the cosine of 270? 0. So 0 times 3 is going to be 0. What about the sine of 270? -1. So 3 times -1 is going to be a -3. So now I have my coordinate 0, -3. The axis values on the polar graph correspond with the axis values on the rectangular graphs. So if I'm telling you that this is 3 steps in the direction of 270, that's 3 steps directly downward, which when you plot 0, -3 on xy axis, that coincides. It should make sense. All right. So that's how you go the one way. Let me show you how to go the other way. So I'll put a star on the second problem. Well, second problems. Because in the case of number 3, we're given x and y. And I want to come up with r's and betas. Well, just looking at all of my information above, I can see that I have a formula that solves for r in terms of x and y right here. And I have a formula that solves for theta in terms of x and y right there. So I'm gonna snag those two bad boys and bring them down into the party. All right, so r is equal to the square root of x squared plus y squared. Theta is the inverse tangent of y over x. All right, so zero squared plus -49 squared. That's going to give me a 7. And then for the other one, oh, sorry. It would have been 49. Yeah. It's one of those where I put the answer in the question. Whoop. Which is 7. Thank you. Inverse tangent, -7 over 0. All right, so I got the r value. The theta value is a little trickier numerically, but if you consider the nature of the problem, you probably already have it. So tangent here is undefined. So you'd be asking yourself, where on the unit circle is the tangent undefined? Happens in 2 places. And this question's calling for degree answers. All right, so just going around the unit circle, where would you expect tangent to be undefined?
2.
Pi over 2 and -pi over 2. So we would say 90, to keep it in this domain, 90 and 270. All right, because they're calling for 0 to 360. All right. So if I were to plot this set of coordinates with 0, -7, so if I were to plot that on the rectangular coordinate system, 1, 2, 3, 4, 5, 6, 7, it would be somewhere around here, 0, -7. I couldn't find a graph grid that was big enough that looked this cool. Yeah, it's going to be 270. Exactly. Oh, it didn't even come out on the paper at all? Oh, that's cool. Oh, that's the best part. You see what I'm going for though, right? Yeah. I mean, it's glorious. You look at it, you're like, oh, that's how it all works. Like, you see the rings coincide with the rectangular coordinate system, but only on the axes. It's beautiful, but it's not on your paper, so that sucks. All right, well, note to self, I guess. All right, yeah, but 270 is the winner, because if I'm traveling around this circle, to get to that location, I'd have to go all the way around. All right, so I'm looking at 7. My final answer would be 7, 270 degrees. Normally I'd say yes, but because this problem gave particular constraints, we'd be stuck. Such a nice looking guy. So we're converting into rectangular form because we have it in polar form. So we're looking at, I'm going to go with this one. We're going with the R value and a theta value, and we need to get that converted over. So I'll show you in a minute a little calculator technique. Some folks find this to be unnecessary, but I'll show it to you anyway, because I figure, you know, the more tools you have in your toolbox or weapons in your arsenal or whatever the friggin' analogy is, it's fine. The better off you're going to be. So x equals r cosine theta, and y equals r sine theta. So -2 cosine of -5 pi over 6. And the same thing, just with a sign for the y value. All right, and so then we just have to crunch these numbers, which involves some unit circle knowledge. Sometimes just getting the positive coterminal angle is enough to get you kind of oriented. So this is the same as 7 pi over 6. Now, for now, the calculator can be a resource, but I'll show you in a sec. I mean, in terms of actually just typing in cosine 7 pi over 6, sine of 7 pi over 6. But 7 pi over 6 is 210 degrees, if that kind of places you a little bit better. But I'll just draw out the relevant part of the unit circle. So we're talking right here-ish. And so the coordinates at that location, because again, it's 210 degrees. Let me clean that up a little bit. It's 210 degrees, but that means it's a reference angle of 30 degrees. So our coordinates would be some variation of radical 3 over 2 comma 1/2. It's just a question of signage. Because we're going left and down, it's negative, negative. Coordinates on the unit circle are always cosine comma sine. So we have our ratios. And from this, you get the idea that if you really just know the first quadrant of the unit circle, you pretty much have everything you need. All right. So we're talking -2 times -√3/2. And then -2 times -1/2. Clean them both up, and we're talking radical 3, comma, a solid uno. All right, so that would be your rectangular coordinates consistent with this set of polar coordinates. So, there's a lot of background work going on here, but, it's still very manageable. All right, so in the angle menu, which is, so the background of it looks slightly different from your calculator, but it's the same calculator. There's some subtle differences because this works on a touch screen. There's no zoom button on my app, but yeah, it's pretty user friendly. This is the X84 app. So if you wanted to have a graphic calculator on your smartphone, obviously you can use that during a test. Hopefully one of these days I'll be able to not make that statement, we'll have some sort of security in place for that. But at this point, unfortunately, it's an obvious statement. You can't use it on a test, but if you don't want to carry your calculator around with you, if you're taking a bus or you got a lot of places to go, and then this could be the option for you. So it's the X84 app. You can download it immediately. The X84 is the light version. There's a paid version that costs, I think, like $5 or something like that. I don't know if that's necessarily what you want to do, but it's got a lot more features, so it might be worth it. So the angle menu is second apps. So second apps brings you into the angle menu, and then you have all these options. So it's just my app has like little cheat codes that remind you like what everything's represents, but your calculator has all these functions too. So degrees, minutes, and then it has angles, and then it has DMS, so to convert to degrees, minutes, seconds, but that's not really what we need. What we want are the last four options. Rectangular to polar R, rectangular to polar theta, polar to rectangular X, polar to rectangular Y. If you select the appropriate one, it'll convert from one form to the other for you. The only thing is it'll put it in decimal form, but you can make the adjustment from there.
Sorry, I just got that. What are you doing first screen to get there?
Second apps. So that puts you in the angle menu. All right, so to get the X value, so I want polar to rectangular X. So I'm going to select option 7. And then I'm just going to type in what they gave me. The thing is, I got to make sure I'm in the right mode, all right? Because my calculator and the problem need to agree with one another. So if I'm in degree mode, so I'm in radian mode, so that's good. But if I were in degree mode, I could do it one of two ways. Either to convert it over into radian mode or convert my angle into degrees. Either way is going to work, all right? But it's already in radian mode, so I'm going to leave it as is. So I just type in my ordered pair exactly as is. It's going to bring back the X value. So -2, comma, and then -5 pi over 6. So it's going to spit back the X value. I'm going to hit enter. In decimal form. So you may look at that and say, well, I need the exact value. So this is just like trig class where my calculator gave me all these decimal values, but I needed the exact value. So what do I do? Well, I always have it in my mind that whenever I'm dealing with a trig problem, radians are always some product of pi. So if I get a decimal, it must have been something multiplied by pi. But if I'm dealing with a ratio and I get a decimal, some funky decimal, It's the square root of something. So square it and see what it's the square root of. So, you know, you run into this issue fairly frequently with the calculator, where it doesn't give you the exact value, but it gives you enough for you to be able to make a reasonable judgment of what the numerical value is. 3.0000000000149. Okay, it's trying to say 3. All right. So I just squared the decimal. So to undo that, I'd slap a radical over this, giving me the radical 3. So if I wanted to find the y value that corresponded with that, I can go back up and choose the other function. So second apps, option 8. All the other parameters would be the same. Hit enter. And that one's going to be just a clean 1, so we're not really worried about that. All right, but that's pretty nice, you know. If you know how to navigate the calculator, there's usually a shortcut or a hack in there for you. Like, for example, in number 4, we need to go to polar form. So the way I'd handle that would be to go second apps, option 5, and then type in 2, 2 root 3. Hit enter. So I got a 4. All right. Then hit the up arrow to bring up that last calculation and hit enter on it so that you can repeat it. And then just overwrite the R to PR with an R to P theta. So second apps, option 6. And then enter. And so we get this number. Now I'm looking at that and saying, okay, so I know I'm looking for an R and a theta. That theta should be some multiple of pi. All right, so this is pi times something. All right, let's see what the something is. Let's divide out the pi. That's 1/3 even without hitting math frac. So I divided out the pi. I got 1/3. Bring the pi back in. So now I know that my value is going to be 4, pi over 3.
You see second app 5, I think second app 6.
Second app 6. Yeah, so I said 5, but I did 6. So elements of what I did was correct.
Just for information, the free app doesn't give you option 2, 5, 6, 7, 8.
Well, that sucks.
Yeah, you gotta upgrade Pro.
You gotta pay the $5 to get all the extra, all the useful stuff. So it'll let you add and stuff, basically. Maybe make a graph. I knew that there were some limitations on the modes that it may not, like you can't convert into a parametric mode in the free version. So yeah, they want you to pay.
So after,
As you can see, I paid. So
after you got that, the 1.047, what did you have to do?
well, I knew it was some multiplier of pi because it's a radian value. Divide it out, multiply it back. And that's the workaround. I mean, anybody that has deficiencies in unit circle trig, you know, like ultimately I want you to be able to get stuff right in Calc 3. Yeah, you should still work towards understanding the unit circle, but you can't just take a loss on everything trig related just because you don't know that. So your hack is, all right, well, I don't know what the sine of pi over 4 is, so I'll put the sine of pi over 4 in my calculator. I know it's the square root of something, so square it. 1/2, pop a radical over it and simplify. So 1 over root 2, or radical 2 over 2 if you rationalize. All right, so it's a way around it. Same idea going the other way. Let's say you need to know the angle corresponding with, I don't know,
Tan inverse.
the inverse tan of, let's keep it simple, we'll go with 1. And you get that. And you say, okay, well, I know it's some radian measure. So it's something times pi, so divide out the pi. 0.25, bring the pi back. 0.25, 1/4 pi, pi over 4. Right? So there's ways around it. The thing is, if you're given an entire unit circle that you need to fill out, to do every single part of it that way, it's very time consuming. And also not really demonstrating much knowledge. So you want to work towards one while you're buying yourself time with the other. Right? This skill buys you time to learn the other stuff, the unit circle. All right. But I mean, there's also the component where you look at this and say, I used the calculator in my little shortcut so that I didn't have to do any of that. There's that part of it too. Sometimes you just want to take a problem that requires thinking and make it mindless. That's part of the fun too. Knowing and recognizing where you can cut corners, that's part of the program. You're probably going to be required calculator. So here we're saying that the radius is 3 regardless of what theta is. All right, so if theta is 0 degrees, it's still going to be an R value of 3. If theta is 30 degrees, it's still going to be an R value of 3. If it's 90 degrees, and so on, all the way around. The bottom line is, what you're going to end up with is a circle. Undo. What you're going to end up with is a circle. That was good, but now it's filled in. Address the opacity here. None. What you're going to end up with is a circle. And that's really all there is to it, because you can go 3 units in any which direction, it's still going to put you somewhere on that path. Alright? If you had an R value of -3, that would mean no matter what angle I was looking at, I was taking 3 steps in the opposite direction. Bottom line, still going to be a circle. So if R is equal to 3 or -3, it's going to be the same path. Same path as R equals -3. Now this one is saying theta is equal to 3 pi over 4. Implied that that's for all values of R. So for all R. So no matter what my R value is, my theta is always going to be 3 pi over 4. So R could be 1, it could be 2, it could be 3, 4, 5, it could be -1, it could be -2, -3, -4, -5, -infinity. Now this is circular, but this is theoretically it's in 2 dimensions, so it would be infinite. But when we span this out to 3 dimensions, there's my line. When we span this out to 3 dimensions, you're going to see that this really ends up being, every one of these lines that look like lines here will end up being circles, right? Because, if you're close enough to a top view of the planet Earth, it's all going to look flat, right? And if those longitudes were actually traced out on the surface, they would look like lines. But then as you pull back, it looks more spherical, and those lines you see are really just straight circles, right? And so that's what's happening here we're just looking, and 2 space is really just a microcosm of 3 space. Alright, so if you're just looking at 2 space being defined as an infinitesimal size little segment on the surface of 3 space, then you have a true understanding of what 2 dimensions are. But really, it's just like the whole, like the ant's perspective. If an ant was on your arm, a person standing on a planet, that kind of thing, size relationships. Right. Now, your calculator understands polar graphs.
I'm sorry, if you graph the line for negative 3 pi over 4 would be 4 x.
If it were negative 3 pi over 4, it would be what?
It would be just the opposite of x.
Yeah, exactly. Exact and window. Your calculator understands polar coordinates also. So let me take a second and share that with you. With my clunky calculator interface. Oh, my face. Hello. Now everybody knows what I look like. All right, the likes are gonna come pouring in now. I could have lived every day of my life without that happening. We'll see. If you go to mode, again, function, we were in parametric, you can go to polar. Hit enter on polar. Now go back into y equals. It's not y equals anymore, it's r equals. All right. Let's move that over a smidge. All right, the first graph that we were looking at was r equals 3. That's something the calculator can understand. Theta equals 3 pi over 4, you're on your own. Calculator can't handle that one. All right. So, r equals 3. Start with a zoom 6, zoom standard. Now, it should, in theory, look like a circle, but just based off of the rectangular pixels and everything, it always ends up looking elliptical. But if you count tick marks, you can see it's 3 in each direction, so it's supposed to be circular. But the scale is a little off. You see it's more compressed along the y-axis. Right, so you can play around with it to make it look a little bit more circular in terms of the dimensions of your window, but I don't think that's necessarily worthwhile.
You could use zoom 5. And it makes
The zoom box?
Yeah.
Oh, zoom square, yeah. Yeah, there you go. Very good. That was literally the first time I ever used that one. I've never used zoom square before. Looks much nicer. What did it make the window? Yeah. Because that's precisely what we would have considered. In order to make a square window, it needs to go from about negative 16 to 16 on the x-axis. It's like, well, why'd you do that? It doesn't make sense. So, but it looks nicer, and oftentimes that's all we need. Now, in terms of the window, because the window is always going to be important. Data step behaves a lot like t-step in parametric mode, in that if you make it too big, it starts cutting corners in how it graphs. So if I make this theta step, let's say I make it, instead of 0.13, I make it like 0.3. It's a little bit, well, it cut it short, but it's supposed to be a little bit boxier. Let me make it look obnoxiously larger. I'll make it like 1. All right. So every 1 radian is plotting a point and then connecting with straight line segments. It only simulates smoothness because when you plot it for a very small theta step, it's plotting every one of those little deviations of theta. So if I say go by 0.01, then every 0.01 of a degree or radian, depending on the mode, it'll plot a point and then connect those, so it simulates the appearance of the curve. Right? So if I make it too large, it's not going to show anything. All right. If I make it too small, it takes forever to graph. All right, it gets there, but it takes a while. Hit on to interrupt if you get into that jam. So, like a 0.1 usually is a pretty good way to go. All right, it's kind of a combination of accuracy and speed, so efficiency by definition. Now, the theta min, theta max is you telling the calculator what theta you want it to start off with and where you want it to end up. Next class, we're going to get into more detail on under what circumstances that's not going to be 0 to 2 pi, because that's what it defaults as. But I'll show you really quickly. If I make this 0 to pi, I only get half of the circle. All right? But depending on the nature of the function, I may not even get that much. Right? If it's some weird trig function, I might not even get half of the overall function. I might only get a quarter of it or something like that. All right? So we'll talk about why that works the way it does and how to navigate that. But for now, I just wanted to go through one more problem, then I'll let you go. And that's related to these bad boys. You're just converting entire equations over from one form into another. The reason I brought up the calculator approach is because it would be really nice to be able to check your work or at least have a sense of what you're aiming for. All right, so for the first one, you just go back to all those formulas that we created on the previous page and just grab one that seems to make sense. So in the case of sine, for example, I want that to go away. I also want the r to go away. But let's just focus on the sine for a second. One of our rules is that y is equal to r sine theta. But by extension, or at least going back in time, that's equivalent to sine of theta is equal to y over r. So I can manipulate this to say r plus 5 times y over r is equal to 0. Our only goal is to get it into rectangular form, so x's and y's. Whether you go the distance and get it into some recognizable standard form is up to you. But once these r's go away, I'm going to be in pretty good shape. The one concern I have is that if I were to do the direct substitution here, I would be putting this radical in two separate locations. I feel like that's going to end up being ugly. So I'm going to clear out that r on the bottom by multiplying everything by r. And that's going to make r squared plus 5y equal to 0. And just going back to this formula here, r equals the square root of x squared plus y squared, I can square both sides and make that r squared, bless you, is equal to x squared plus y squared. All right. These are all, I mean, even the ones I'm writing are ones that we wrote on the previous page. It's just, these are the standard formulas that textbooks usually give and things like that. I'm just showing you how you could vary them to make them more suitable for our needs. Because I'd rather put the x squared plus y squared in here once than to put a radical x squared plus y squared in there twice and make a mess of it.
You don't simplify it anymore.
No, you don't have to simplify it anymore. If you were to do that, you would complete the square to make it an equation of a circle, but it's not necessary. Because again, I try to balance like what skills are useful and what like you could benefit from. In this case, I mean, we could spend some time converting it over, but it doesn't really advance the plot. Because in reality, if you were to graph this, the whole point of this lesson is for you to say, you know what, regardless of how that one shapes up, if I'm putting this in my calculator, that's the one I'm going with. Because I can solve that for r real quick. Just subtract that and type it in, and then I'll have my graph. All right, and so you'll be able to see very easily what kind of graph it is. So I'll put a star on the second one, which in terms of difficulty isn't really much more complicated. I'll tell you, some of these problems become a lot more complicated if I ask you to simplify. So, I mean, there's that, but again, it doesn't really do much for us. The last one, number 9, is going the other way. For this one, we would want to distribute it out. So x squared minus 8x plus 16 and plus the y squared equals 16. I'm going to put a star on this one while I'm here. Now you see the 16s cancel immediately. Boom and boom. I can rewrite as x squared plus y squared minus 8x equals 0. By definition, x squared plus y squared is equal to r squared. And x is equal to x is equal to r cosine theta. The 8 was already there. X is not equal to 8 because that doesn't make any sense. Alright, so this is in polar form. Technically perfectly acceptable in terms of a final answer. But we can go a little bit further. Might as well. I have a common r that can be factored out. And if I set each of those factors equal to 0, I get r equals 0. Now, in function notation, so like a rectangular coordinate system, if x was equal to 0, we'd be talking about a position, right, within the coordinate system. When r is equal to 0, we're talking about a circle with a radius equal to 0. Is anything even there if you have a circle whose radius is 0? Does it even exist?
No.
No. So this is irrelevant. So we're left with the r equals 8 cosine theta equals 0. And then we can solve that for r, and you get r equals 8 cosine theta. So a little bit cleaner of an answer, a little bit more calculator ready. Would you have to do that on a test? No. You stop right here, call it a day. But I just wanted to take a minute to talk about that r equals 0 part of it. Because in the xy coordinate system, if x is equal to 0, y is equal to 0, that's a place. All right? That's a location. It's position 0. But in the polar coordinate system, it's a distance. All right? A circle with a radius of 0 is not a circle at all. It's nothing. All right? So it's not even a geometric figure, so it's irrelevant. All right? So that's where we're going to leave it tonight. If you have any questions, stick around. Otherwise, have a wonderful, wonderful weekend. I'll see you on Monday. All right, so on the next page, we had those beautiful calculator hacks and all that, but now what's that going to do for us when we got to actually use formulas to convert over? All right, so the first thing I like to do, and this is an algorithmic approach that I follow. It varies from person to person, but I always feel like if I can get rid of the theta, that's going to put me in a good spot. So I always look at my expression and see how can I get rid of the theta. If it's not obvious, then I'll move on and try something else. All right, so r minus r times sine of theta, by definition, is equivalent to y over r. And so I have a little cancellation here. A couple of r's will cancel. That's nice. A little byproduct. You know, I didn't go in looking for that, but I'm happy to accept it. All right, so r minus y equals 0. Now, since our goal is to get into rectangular form, we're right there. Because I just have to get rid of r. R is equivalent to the square root of x squared plus y squared. Now at this point, you kind of decide where you want to go from here. This is never going to be a standalone problem on the test because there's no calculus in it. So this would be part of some other type of question. But really our goal here is to kind of determine the efficiencies associated with different forms of functions. So just looking at what I have here, without even considering what I would do as a next step, it seems that this is probably the better type of function to work with. Like if I had a choice between a form, this one or this one, I would probably lean towards this one because this one looks like it's shaping up to be a mess. Now, when you clean it up, so I would call this a final answer, by the way. Perfectly acceptable final answer. But if you decided to clean it up, if you wanted to go further, you could add y to both sides and get the square root of x squared plus y squared equals y. Then raise both sides to the second power and get x squared plus y squared equals y squared. Simplify and get x squared equals 0. And then simplify further and you get x equals 0. So after all that, it's like, wow, okay. Well, maybe I do want the function form. That's much simpler than what I started with. But then you think about it and say, well, I had to do all that work to get there. So is it really worth it? And then add to that the fact that I just have to make maybe like 2 little maneuvers to get this in R equals form. There's no way that I can take this and get it into y equals form. So this is not going to be calculator ready. That being said, it's just a vertical line, so I don't know that we needed to be calculator ready. The point being, we have a simple answer here, but it took a lot to get that simple answer. Sacrifice a little simplicity for efficiency, really, more than anything else. All right? And calculator understands polar form. So it's going to understand that R equation just as well as it would understand a y equals equation. All right? Now, for the next one, we have a hyperbola. Let's see what that's going to look like when we convert it over into polar form. Just going to move this up. A little stray mark doesn't seem to want to go away, so I'm just trying to... There we go. And then it came right back. I'm going to get over it. That's all I'm going to do. I'm just going to let it be. All right, so... slightly bigger on the parens. By definition, x is equivalent to r cosine theta. And y is equal to r sine theta. That was nice. That was nice. Yeah, again, the idea is that once you get it into r's and thetas, we're done. So put a little box on that and call it a day. However, the idea again is that it's probably not going to be a standalone problem. You're probably going to need to do some calculus to it, maybe graph it. So it's in your own best interest to be prepared to do something with this. So we might as well take a little bit more of a look at it. So r squared cosine squared theta over 4 minus r squared sine squared theta is equal to 1. Now, we can get a common denominator, but my preference when it comes to fractional equations is to clear out denominator. So I'm going to multiply through the 4. So 4r squared cosine squared theta minus, that would just cancel. It's just r squared. The other one gets the 4. 4r squared sine squared theta is equal to 1. Is equal to 4. Man, all over the place. That's what happens when the Giants suck. I wonder if I could do a study on that. Just go back over the years, look at the seasons the Giants have done well, and look at my recorded lessons. Just count how many like little blunders are in there. Probably never made a mistake when the Giants are winning. And then this happens, and all of a sudden I can't even multiply 1 by 4. See, it's falling apart. It's all coming apart, off the rails. All right, I pull out the r squared, and you have cosine squared theta. I have to look forward to the Knicks.
Oh,
So just we'll put it in perspective for you. I got to look forward to the Knicks. The Rangers, I guess.
Yeah, sport is in
So I pull out the r squared. I could divide both sides by everything but the r squared. I'll be looking at r squared is equal to 4 over all that jazz. And then I can take the root of both sides. And so I'd have r equals plus or minus. I'll make it a 2 on top over the square root of cosine squared theta minus 4 sine squared theta. All right, the benefit to this, as opposed to what I boxed above, is that this is calculator ready. I can pop this in. All right. The plus or minus is really just there to indicate direction. Okay, so which way you're going around the path. So if you're just concerned with the path, you don't need the plus or minus. But if you're concerned with movement along the path, then you would need the plus or minus. Right? Because depending on a physical situation, if it's a word problem and they give you some constraint, they tell you that the object's moving in a counterclockwise fashion or clockwise, then what the R value would be in terms of positive and negative would matter. Right? So you look at this, you say, well, I did an awful lot of work to get it in this form to get it to be calculator ready. Couldn't I have just done that with the original function? Sure. So yeah, this is one of those kind of problems where you could go either way with it. Depending on what the instructions tell you, you may not have a choice, but if you do have a choice, I think it's just as much work no matter how you slice it. So, I don't think we drew any kind of meaningful conclusion from the conversion of this one, whereas in number 9, for example, I think it was pretty clear that we would want to go with the polar form because the rectangular form is a mess. Okay? If you solve it for y, you get the plus or minus in the radical, but this is a pretty elegant looking answer. Okay? So it's all going to depend based off of just what the outcome is. But you don't go into a situation from here on out thinking, all right, well let me just see how it goes. The idea is that we do that in class so that when you come across a situation, on a test or a problem set that you're working on your own, you would say, circle, I want to go polar form because when we did it in class, that worked out nicely. Hyperbola, it was a mess on the way. So, pick your poison. It doesn't make a difference, So you can kind of decide based off of your experiences in class how you want to apply this stuff moving forward. All right. Now we have the classical curves. Crazy because I came in today and I saw a classical curve right here. It's a transformed classical curve, but it's pretty much the right idea. Let me send that out real quick. This might fall into the category of like, you look back on this picture, like a few weeks from now, you're like, he sent a picture of a rubber band. Why did he send a picture of a rubber band? But yeah, that's what I did. Right? Because what this picture is really getting across the idea of a Lima song, or Lima song, is actually how it's pronounced. But like, I can't not see lima beans. So I see that and it's Lima. Now I do remember one of the like the 4 things I remember from French class, all 5 years of French. That little almost number 5 underneath the C, that softens the C. It's Sevilla, I think. But whatever. But that little symbol, it takes a hard C and makes it a soft C. So it's definitely son. But the Lima or Lima, I leave that up to you. The other ones I think are pretty obvious. Rose, cardioid, those sound about right. This one, the way you would make up the phrasing, the pronunciation of it is exactly how it's pronounced. Lemniscate. Like that's just what it is. Right? And then the spiral of Archimedes. Right? I suppose the last one you wouldn't know how to pronounce if you'd never heard of Archimedes. Right? Or ever seen that word written, or I'm sorry, spoken out loud. I had that experience because I read a lot of books when I was younger, but I never heard the word spoken out loud. So like A-W-R-Y, or rye. Yeah, I thought it was Ari, because I'd never heard anybody say it before. And we didn't have like Google pronunciations, like you type the word in and you just click on it and it says it for you.
Those don't even always work.
Yeah,
Sometimes they can be like the British version or the Australian, and it's like, this is not.
it's complete hit or miss sometimes. But yeah, there's some words I look at, I'm like, oh wow, that's how you say it. And it's like 30 years later, so it's entirely possible. But the moral of the story here is, I mean, it really doesn't matter what these things are called. It's more so that there's an equation that corresponds with a picture. Now you may look at it and say, okay, well, couldn't I just put the equation in my calculator and then learn the characteristics that way? And then my answer to that would be like, yeah, that's a great idea, let's do that. All right, so let's take a look at number 11, r equals 3 plus 3 cosine theta, and see how one might go through the process of graphing it in their calculator. All right. Understanding that it is definitely a little on the, I don't want to say tricky, but it's a little different than the way you would create a graph in function form, or rectangular form, because when you would go to the table to grab some points, even if it was a decimal, you still know it would be left or right and then up or down. All right, there wasn't as much guesswork involved. Here, there's a little bit more guesswork. So let's investigate. All right, so I don't know why. Maybe that's why I put it away. All right, so I'm putting mine in polar mode. All right. Radian. Yeah. Now you really have license to go either way, because when I told you that I was going to give you this graph as is to create your sketches, that tells you that you're going to get the radians and the corresponding degrees. So you want to work in degrees, work in degrees. You want to work in radians, work in radians. The only time you need to be in radians is when you're dealing with a non-trigonometric function along with a trig function. Right? So let's say you're in function or a rectangular form and you want to graph y equals x squared, keeping it simple, along with some trig function. Right? Because the units don't jive if you have your calculator in degree mode, because then the scale goes up to 360 degrees, and then your line's going to be all out of whack. All right? Or in that case, your curve. So yeah, you want to be in polar form. radian if you don't feel like changing it, And so that's what I'm gonna do. Y equals, again, becomes R equals. So 3 plus 3 times the sine of theta, times the cosine of theta, sorry. Now, there are characteristics related to these classical curves that allow you to come up with a sketch without really doing what we're about to do. But this technique is always going to work, so there's that. But also, you want to have a way to investigate these characteristics on your own, not just have, a chart to rely upon, all right? So I'm going to hit graph, take a look at the picture. Now, again, so this is where my app differs from your calculator. I don't have a zoom function. I just have a thumb and an index finger. So I can get it sized up the way I want by doing it that way. All right, so let's say you don't have a touch screen to work with. Zoom 6, standard zoom. All right, let's see how it goes. Zoom box, yeah, zoom box will work. Yeah, so just as long as it's going to be around 0, and that somewhere in that -10 to 10 neighborhood, you're going to be fine, because none of these graphs are extreme in terms of their scale. All right. So yeah, so there's that, and you can also manually manipulate the window, but I would say you hold off on that idea until after we talk about what about the equation tells us certain attributes of the graph, right? So what we're going to do is create a table of values, because I got to get this on paper. So the table of values is, it's as easy as you want it to be, basically. It's kind of tricky, though, because it does call upon prior knowledge, and that prior knowledge has everything to do with the unit circle. All right. Now, one thing that's kind of a little bit of a weird component is when you plot coordinates, x comma y, x is treated as the independent variable and y is treated as the dependent variable. Right? But here you plot r comma theta, but theta is the independent variable. Right? So it works the other way around. So what I want to do is I want to grab some theta values. I want to grab me some theta. And I'll start it off at 0. And I'm going to start working my way around the circle. And here's the important ingredient. I'm going to use only convenient values of theta for cosine. And you're like, okay, the hell does that mean? So thinking in terms of the unit circle, at least to start, I only want values of theta that are going to give me cosine ratios that are nice. Nice. So basically, I don't want radicals, because radicals means decimals. Decimals mean estimations. Now, I might resort to that, and that's perfectly fine, but I don't want to go to that as a default, all right? So the first relatively clean one is pi over 3. And that's because cosine of pi over 3 is equal to 1/2, all right? Another one is pi over 2. So it's going to boil down to the quadrantals, so anything on an axis, and anything that has a denominator of 3. All right. If this were sine, I would go with denominators of 6, because pi over 6 is clean for sine. But if I did pi over 3 for sine, I'd have a radical 3 over 2. I don't want that. Now, there's nothing wrong with it. If you grab that value and you got a decimal and you had to estimate, you did not do it wrong, I promise you. It's just, it's not a nice set of numbers. Right? So that's really what we're after here. All right. So next up would be 2 pi over 3. then pi, and then so on. So I'll leave it at that for the moment, because where I'm at this point, I just want to see. Yeah, I think I'm gonna have to switch over to the ordinary graphing calculator, because what I'm about to show you is not gonna work on this. What can you do? What can you do? So, in your window, so second window, table set, we're gonna change. So this is not the ideal approach, but this is the way we're gonna do it. We're gonna change our delta table. We're gonna make that pi over 12, so that it counts based off of what we have in the on our graph grid. So you're gonna change you're gonna make your delta table pi divided by 12. And then go back to the table . The start should have been 0. I don't know why my start isn't 0. There we go. Now it's 0 for some reason. I have no idea. All right. So again, not ideal. I'll talk you through the other approach in a couple minutes, but for now, I'll just get you going on this one. Every line segment up from the polar axis is equivalent to pi over 12 units. So pi over 12, 2 pi over 12, 3 pi over 12, 4, 5, 6 pi over 12, and so on. So all you're doing is counting down steps corresponding with the position here. All right. So I'm taking it a step further and only grabbing the convenient ones. All right. So 0 pi over 12 I know is 6. Then 1, 2, 3, 4 pi over 12 is the next one that I want, the pi over 3. So 1, 2, 3, 4 pi over 12, that's 4.5. All right, so it's taking all of my need to do any calculation out of the equation here. So 0, 4.5, 2 more movements, and I'll be at pi over 2. So that's 1, 2, and that gives me the 3. All right, so all we're doing is counting. What we're not doing, and this is the important thing, what we're not doing is any thinking. All right, all the work is mechanical, it's rote. All right, so 2 more steps, go down 2 more steps, see what comes up. 1.5. I'm at 2 pi over 3. 1, 2, 3, 4 more steps will get me to pi. And that's going to be 0. Now, you could look at it the other way, because, and that's kind of the moral to the story here. We came up with these values based off our knowledge of the unit circle. Find the clean ones for cosine. But by establishing the step, the change in table as pi over 12, we made it so that the theta is going to increase corresponding with movement around the polar graph, which is great. The nice byproduct of that is it allowed me to just go through my R column and say, you know, I only want the clean ones. Now I can go back the other way and say, all right, I had no idea what the angles are supposed to be, but I do know that X number of units corresponds to 0. And so now I can plot the points that way.
I got 6 for 0.
You got 6 for 0? Oh, I think I did 2. I think I just wrote 0 for some reason. Let me just go back up. Yeah. Because in retrospect, that felt right. All right, so what that also tells me is that the table of values is more of a luxury than anything else to kind of get a feel for things. I can just work off the table in my calculator. Now, what I was going to show you on the graphic calculator has to do with actually deciding on these values first. Once you decide on them, you can, in your second window menu, change it from auto to ask. And then it allows you to just type in what values you want and create a table, a unique table of values that way. It's just this doesn't seem to have that setting. So, and for whatever reason, I can't show it to you on this because every time I put that in, it hijacks the whole feed, and I can't display the computer monitor anymore. And this is literally the only room that happens in. So I don't know what's wrong. Anyway, we'll do it this way for now. In next class, before I hook up the iPad, I'll try to show you the other technique. So I could go down my list and say, okay, I have 6, 0. That's 6 steps in the direction of the theta value of 0. So here's the theta value of 0. I'm going to go 6 steps in that direction. So 1, 2, 3, 4, 5, 6. So it's going to be about right here if I'm ballparking it. All right. The next one that's important, I mean, I guess they're all important, but the next one that I care about, because remember, these coordinates are written as 6, 0, 4.5, pi over 3, 3, pi over 2, 3 halves or 1.5 if you want, 2 pi over 3. It's always r then theta, 0 and pi. So the second one is telling me that I'm taking 4.5 steps towards pi over 3. So towards pi over 3, 1, 2, 3, 4.5. 3 steps towards pi over 2. 1.5 steps towards 2 pi over 3. 0 steps towards pi. Well, 0 steps towards anything is going to leave you at the pole. Now, I only came up with these points, but my graph looks like that. So what we're going to do is rely on symmetry and a little bit of common sense. Well, maybe the common sense first, then the symmetry. Because it's got to look like this. It seems as though we have the top half of that. All right, well, in order to look like that, it would have to be basically a reflection in the bottom half. So I'm going to reflect all of these points over the polar axis, and that's going to give me the bottom half. Now, if I didn't want to do that, that's fine. I could just keep going down my table, just keep in the down arrow, and grab more and more points, and eventually I'll have everything I need. But if you can kind of make that realization, you can save yourself a little bit of time. All right? So the important angles, that's how you're going to get your reflection. So let me highlight. We're looking at pi over 3, which means we're also looking at 5 pi over 3. We're looking at 2 pi over 3, which means we're also looking at 4 pi over 3. All right, we had pi over 2, which means we also need 3 pi over 2. All right, so reflect the angles and then use the same steps in those directions. All right, so we did 1.5 steps towards 2 pi over 3, so let's do 1.5 steps towards 4 pi over 3. We did 3 steps towards pi over 2, so 3 steps towards 3 pi over 2. 4.5 steps towards pi over 3, so 1, 2, 3, 4.5 steps towards 5 pi over 3. And then a nice smooth curve through all of it, and then you have your boom shakalaka moment. Now, that's the best I can draw, so. The good thing is I won't hold you to any standards that I can't hold myself to. So if your graph looks even in the neighborhood of that, it's a full credit graph. All right. So you have this picture, it corresponds to this equation. You compare it to the table above, and you start asking, okay, well, what do they just graph, and why is it important? All right, so we're looking at different possibilities. I might as well bring it in a little bit because it's hard to see. But we have one that talks about a plus a cosine theta, a plus a sine theta. And that's your cardioid, all right? Now you can see that the limacon has similar characteristics, except it requires the coefficients to be different from one another, all right? So it is possible that you could have a limacon that looks very much like a cardioid, but in order to be defined as a cardioid, the coefficients have to be the same. So if you think of the cardioid as a special type of limacon, where first off, there's no inner loop-de-loop, so visually that's your difference, but also you're talking about something, where the coefficients would be exactly the same as opposed to being different. So same structure, but same structure, but also same coefficients, making it a cardioid. Am I going to ask you to name these things? No. So it really doesn't matter in that regard. But if I start using these terms in class, I don't want you to be caught off guard. Also, we start getting into things like horizontal and vertical tangents and the calculus of it. If I start getting into derivatives, I see I have a vertical tangent here and here. I have a vertical tangent there, so 3 of them, and horizontal tangents here and here, and I even got a cusp. So there's a lot of calculus going on in this one diagram, right? So we're gonna have to investigate that stuff also, all right?
I see on the board that for the limacon still is an addition for the sine theta, but on the printed copy we have a negative. Or you put it A negative B sine theta. Is that a plus?
It should be a plus. Yeah, it must not have come through in the copy.
Oh.
Yeah.
So they all addition.
Yeah. The old picture of a picture business. I got this from some website somewhere. Probably could have typed it up and made it look nicer, but I didn't. All right, so the remaining problems here are all basically doing the same thing, coming up with values to graph and all that good stuff. So I'm going to put a nice star